Okay, so coming at you with the first of a series of videos introducing a new concept leading towards something that's called Demoivre's theorem. I will say that this lecture is probably going to be best in conjunction with being in class already and knowing what's going on with this, so it's not too fast. But honestly, I will do my best to make it as clear as possible. So what I wanted to start with is a review of some information that you have done in previous classes. So again, starting with going to a share here with something that I have prepared. This is called a complex number, 2 plus 2i. Notice that it is of the form a plus bi. So it is technically called a complex number. And unfortunately, because of the fact that it is that complex number, we're going to end up borrowing some notation that we've used in previous classes. So this would actually tell me to, on the real axis right here, move to the right 2 and go up 2 units. So this is the coordinate 2 plus 2i. Now, in a similar way, this problem right here, and I'm going to develop some fairly significant information here, so bear with me. This one would be -5 plus 5i. So again, I'm going to proceed to the left, 1, 2, 3, 4, 5, and then go up 1, 2, 3, 4, 5. So this coordinate right here, maybe I'll call this one A and this one B, went to the left 5 on the real axis, and it went up 5 on that imaginary axis. So it'd be this coordinate right here. Now, some of the problems are really, really nice, and some of them are not so nice. I'm not going to bother to draw this one to scale, so don't worry about that. I went over 4, and I went down 4 roots of 3i. So this is the coordinate 4 minus 4 roots of 3. And maybe the last one right here would be -5 and a -2i. And so it would be sitting down here. Maybe I'll call this point D. Now, one of the things about these points, if we look at them critically, these are all what you would consider rectangular in terms of their posture, because I went over 2, I went up 2, notice that goes over 2 and up 2. So what we have then is very clearly almost a style of an XY kind of a thing. So XY and A plus BI have that very much that same look. But what we have been studying recently is this new concept called polar, where instead of telling you about this value and this value, we go ahead and change the story a little bit, which is why I'm going to change colors to red, where you have an R here and a theta here. Now, the first couple of problems that I have right here are designed on purpose to be related to the unit circle. So, of course, if I went over 1, over 2, and up 2, this makes this thing 2 roots of 2. And the angle that is there, that is the new value of that radius, and that new angle would be the angle pi over 4. But see, if we said just that, it would actually look like it was normal, and there's no way to understand that this is technically a complex number or an imaginary number. So what I want to remind you is that x is r cosine theta, and that y is r sine theta. And so there was this French mathematician named Demoivre that sort of kind of came up with a notation that kind of describes this. And so what he would say is you would start with writing an r, because these clearly have an r. And this is kind of a coordinate of sorts. So you would do cosine of theta, because r cosine theta is the x, plus I sine theta, that's the y. But notice this y value always has an I attached to it. So in this case, what I would do is I would say my radius was 2 roots of 2. And try to keep the red pen going for these problems. 2 roots of 2 cosine pi over 4 plus I sine pi over 4. And now this is what is called trigonometric form. So this is complex form, and this is called trigonometric form. This guy right here again, I would have 5 roots of 2 for what I would normally have considered my radius. So that's 5 roots of 2. Keep in mind, if this angle is pi over 4 right here, then that means the actual angle is 3 pi over 4. So I would go cosine 3 pi over 4 plus I sine 3 pi over 4. And again, that's just trigonometric form. Now, again, I have a series of problems to go through, and I'm going to keep making them a little bit more robust. Notice that if I went over 4 and I went down 4 roots of 3, give me 1 second. Let me stop this and all right, I'm back. I got distracted for a little bit. Mr. Wheeler needed a little something. So let's go back to this little idea, see if I can remember where I left off. But again, going over 4, down 4 roots of 3, that's going to leave us with a radius of 8. So it's going to be 8 cosine. Now, again, what I like to do is I like to look at the easiest ratio that I see. And I can see right here that the cosine is 4/8 or a half. So if the cosine is a half, I'm looking at some kind of a pi over 3 angle right here. So I would use minus pi over 3 plus I sine minus pi over 3. Very important to notice as you go through all of these things, the theta is the same theta. So I use pi over 4 for both the x and the y piece, same pi over 4, same pi over 3. Now, of course, to finish up our story, sometimes you don't get perfect numbers, like over 5 and down 5, that'd be 25 and 4 makes 29. So in this type, that value is root 29, that distance. And as far as finding the angle goes, this gets a little bit tricky, but I'm going to go ahead and use my calculator. I'm going to look at this thing and I'm going to go to angle and I'm going to do rectangular to polar, tell me theta, please. And so if I asked it for -5 comma -2, it says my angle is -2.761, which, you know, if you wanted to, you could add a circle to that, which is 2 pi, to give a positive representation. So it depends on if you want the negative angle rotating down or you wanted the positive angle rotating forward. I'm going to choose the positive one of 3.52 plus I sine 3.52. Now, this is again called trigonometric form. And let me give you just a little bit of extra little information. This number sitting in front right here is known as its modulus. That number, that radius, is no longer actually called a radius in this situation. It's a modulus. So the modulus of the first one was 2 roots of 2. The second one was 5 roots of 2. Then we had 8 for a modulus and root 29 for a modulus. Now, the other thing that I will tell you that is sort of a good and a bad thing simultaneously is mathematicians can be a little bit lazy. And so we like to introduce or create new pieces of notation if it saves us a little bit of time. So mathematicians have kind of created this little notation that looks like this. Since we always keep doing the same stuff the same way, what we have done is they have sort of instituted a brand new notation that is equivalent to this, which is R cis theta. And it's kind of clear that that C stands for cosine and the IS stands for I sine theta, but this is here. And so for this problem right here, if I didn't want to write down all of this, I could write 5 roots of 2 cis 3 pi over 4. And so in shorthand, I'm saying 5 roots of 2 times the cosine of 3 pi over 4 and 5 roots of 2 times the I sine of 3 pi over 4. Again, this one would be 8 CIS negative pi over 3. Now again, all of this sort of seems like, okay, whatever, I got you. I could do that. But there's an extension here that comes from it, because why would we do this? Why would we take these simple values like that and turn it into something so complex? And it turns out there's a really good reason for it that was figured out by some people that were really much more intelligent than I am. But I'm going to kind of take you through what we have right here. So one of the common things that we do is we will call any one of these trigonometric forms Z. So imagine this is Z1. So it's some r cis theta 1, and z2 over here is r cis theta 2. And what if I wanted to take these two numbers and multiply them together? In other words, what if I wanted to take something like this and multiply it together? Now, your Algebra 2 teacher would have told you to distribute, and 5 times 2 is 10. 2 times negative 5i is minus 10i. Then we end up getting another 10i here in the middle, and then a minus 10i squared. We could do a little quick arithmetic and see that this gives me 0 i's, and negative 10i squared is actually positive 10, because remember I squared is negative 1. And so that would give me 20. Now that was a pretty trivial little problem, very, very simple, no big deal. This one's a little bit harder, and I'll get back to that polar thing in a moment. We're going to get there. Now here, when we start distributing this, we get negative 8 roots of 3. Then we get negative 8i. Inside here, we get 4 times 2 is 8. Root 3 times root 3 is 24. So 8 times 3 is 24. So I get 24i. And last, right here, I get 4 roots of 3 times 2 would be 8 roots of 3i squared. Now, when we look at all of that, we can do a little bit of cleanup, and this would be a total of 32 i's because we have that. And right now, 8 roots of 3i squared is actually negative 8 roots of 3, and another negative 8 roots of 3 is negative 16 roots of 3. And so this would be the result of multiplying that out. And that's kind of the way you were taught to do that back in your Algebra 2. But a French mathematician named Demoivre decided that if we could put this in this trigonometric form, so I'm going to try to make this go reasonably quick. I've kind of multiplied this out a little bit right here. So let's see. R times R is R squared. I multiplied the cosines, and the cosine times the sine. So I multiplied these two, those two, and those two. It's just the good old first, outer, inner, last that you have learned. And so these two I wrote here, these two I wrote here, and then the inner and the outer I wrote over here. Now, all of that is well and good, and I just did a little teeny bit of cleanup. So I multiplied this out, and I got my 1, 2, 3, 4th terms from 1, 2, 3, 4 multiplications. Now you'll notice right here we had an I squared because I times I is I squared, but you know that I squared is negative 1. That showed up right here. So you'll notice that this I squared disappeared and it just became sine theta 1, sine theta 2. And then you'll also notice that these two terms right here both have an I in them, so I factored the I out of both of these terms, and I chose to put this one first and this one second for a reason. Now, when you look at that, you might be like, wow, that looks like an awful lot of stuff. But if we look at our card, there's a hint. You see cosine, cosine minus sine, sine is sitting right here. Cosine, cosine minus sine, sine. That's what happens when you add two things together. So this is cosine theta 1 plus theta 2. R1, R2, cosine theta 1 plus theta 2. Now, if you look over here, you see a sine cosine plus a cosine sine, which is right here. Sine cosine plus a cosine sine. That's what happens when you add two things. So in this case, we have the following. Now, again, with our notation that they invented to try to make life a little bit easier, that means when you multiply two things in this trigonometric form, all you do is you multiply their radii or their moduli together, and then all you need to do is add their angles together. Now again, this is going to be a little bit interesting, kind of weird, but I'm hopefully going to make this make sense. So if, for example, you were looking at the problem we did right here, when I took the first problem, I'm going to call it Z1, and I'm going off of the very first question that I got 2 roots of 2, CIS pi over 4. Z2 was 5 roots of 2, CIS I guess that's 3 pi over 4. And again, I'm just grabbing those numbers directly off of these two questions. So I'm going to use the same things that we already have done. So when I multiply them, Demoivre's theorem says all you do is you multiply the radii or the moduli together, and then you add the angles. Well, 1 pi over 4 plus 3 pi over 4 is 4 pi over 4. And this is 2 times 5 is 10. 10 times root 2 times root 2 is 2, and that's 20. And if we jump back out of the fancy notation and put it back, one cool thing is the cosine of pi is -1. And the sine of pi is 0. And you'll notice that that answer right there is exactly -20, which in fact, doesn't look like it quite like what I got here for a minute ago, and I got to figure out what I did wrong. But anyway, that's kind of what is supposed to happen. Cosine of pi is definitely -1. What did I do wrong? Anyway, I'm going to have to figure that out in a minute. Let's see. 2 roots of 2, 5 minus, oh, because 5 minus 5i, I actually tweaked it from the original problem. That's why, because this is actually not what I thought it was. This is the angle minus pi over 4. Which makes this, when they add them together, you get 0. And when you take the cosine of 0, you get +1. And when you take the sine of 0, you get 0. And I got the same answer. Woo, fixed it. Good. Now, this one right here, I'm going to just kind of be a little bit quick about it. This first part, Z1, is at a radius of 8 CIS. It's going to be 2 pi over 3. Z2, this guy right here, has a radius of 4 CIS. Its angle is going to be pi over 6. Now again, you could look at that because moving to the right 2 roots of 3, going up 2i, that's going to have a radius of 4. I can see that the angle here is a half at pi over 6. So the sine is 1/2 at pi over 6. So rather than multiplying them here, I could multiply them over here. And I multiply their moduli together, 32. I add their angles together. 4/6 plus 1/6 is 5/6. But then I can just pop it back out because I know that the cosine of 5 pi over 6 is minus root 3 over 2. And I know that the sine of 5 pi over 6 is 1/2. And lo and behold, you get this answer that we have right here. Now, again, it's arguable whether that was actually worth the time to do something so complicated. But as it turns out, when you do division, it is most definitely worthwhile. Because we're just going to extend this so that when you multiply things together, you multiply the radii, so we're going to divide the radii. And when you multiply, you add the angles. So when you divide, all that's going to happen is you subtract the angles. So when you look at the division case, definitely kind of hard in this version over here. What you were trained to do back in Algebra 2 is you were supposed to multiply by the complex conjugate top and bottom. You were supposed to multiply all that thing out and get this nice, simple set of values. And I kind of decided to use a very similar argument to the one that I have above, but you're going to have all sorts of pieces to deal with. You got -8 roots of 3 first. Then you got a +8i next. Then you got a 16 times 3 or a 48i next right here. And then last, there's an 8 roots of 3i squared that's negative, so +8 roots of 3. And then in the denominator, when you do your first, you get 2 times 2 is 4 times 3 is 12. The outer is -6i roots of 3. The inner, actually, excuse me, 4i roots of 3 here. And then we got a +4i roots of 3. And then last with -4i squared. Sorry if this is going to get kind of cumbersome here, but there's some nice things that are about to happen. 12, those cancel. Negative 4i squared is 4, 16. And up here, we can just do a little bit of cleanup. These cancel, and I just got 56i. Now, again, I haven't actually done this problem already. I just kind of wrote it out, and I was hoping that it was going to work perfect because I'm just running out of time. But in the other version, if you go ahead and go with it, and again, I'm using the same values I have written above. If I consider Z1 as 8 cis 2 pi over 3, and I consider Z C cis pi over 6, Demoivre's theorem says to go ahead and take the two radii and divide them. And I can tell I have a little bit of an issue over here, which tells you how hard that is. If I subtract these, then 4 pi over 6 minus 1 pi over 6 is 3 pi over 6. That's a much nicer answer than what I got. But again, I know that the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. This answer should be 2i. So I can tell I've made a little bit of a mistake over here, and so let me look back at what that was. I got negative 8 roots of 3. I got plus 8i here. I've got a 42 times 4 times 2 is 8 times 3 is 12. That's why. Right here, this is 12i. That's looking better. 4 times 2 is actually 4 times 2 is 8 times 3 is 8 times 3 is 24i. And that's where I made my mistake. This should be 32i. And that reduced very nicely down to 2i. And you'll notice this was very, very difficult to do. This was actually fairly simple to do. So not the best video I've ever done, but it kind of begs how it works. And so I hope that was helpful to you. And we'll go over the next piece later when you start dealing with the extension to Demoivre's theorem, which does get a little bit strange. So again, hopefully this works for you. So in summary, what you can do is if you can take your two x's and y's and turn them into r's and thetas, we have this trigonometric form where you have your modulus and your radius. It allows you to multiply numbers in that form as well as divide numbers in that form. But just like what I did in this example over here, this is done in steps. You get your answer in trig form, and the protocol is usually to rewrite it in the regular old complex form that you've learned back in Algebra 2. So this is sort of a vehicle to kind of go around and get back to an answer in another way, which sometimes is more complicated, but sometimes it's far, far easier. So we'll see some of those far, far easier in the next video. All right, see ya. Have a good one. Bye-bye.